and the chat, just in case. Okay. If you don't mind, please turn on your camera. If you do mind, then don't turn on. Does anybody have any questions at this point?
Can I ask something?
Sure.
Can you hear me?
Yes.
So in the last figure, you mentioned that these lines are not trajectories, but contours of constant energy. Can we draw the, or what would the trajectories look like, especially around the pi point?
So what I said, I think, is that these are not trajectories per se, but they contain trajectories, right? So for most of these, so anything that you start in a line like this will be a trajectory, okay? The contour that you see here is in fact a trajectory. The trajectory has no means of or ways of stopping. I pointed out the distinction between the constant energy level curves and the trajectories around these points, okay? Because if you ask, what is the constant energy level that contains the upright equilibrium position of the pendulum, then the answer to that question is this. I'm drawing right now, this and that together, okay? It is a contour of the energy, but it's not a trajectory, okay? No trajectory will do what I have just shown, because that would mean that it's crossing itself. And as we will see soon, that would already discussed, but we'll see the conditions under which it doesn't happen. So it would mean that it crosses itself, right? So in the phase space, no trajectory can cross itself. So what's the resolution is that, well, what you see here is a separate trajectory. What you see here is a separate trajectory, those two fixed points, right? And this piece here of the level curve with open ends is also a trajectory. And this other piece with open ends is also a trajectory, and the same here, okay? So when I said that level curves of the energy or any preserved quantity are not the same as trajectories, but rather contain trajectories, I was emphasizing this difference, right? Does this answer the question?
Yeah, thanks.
You're welcome. Anybody else?
Yes, if I may. I was just wondering, I remember there was something tricky going on near pi and minus pi with the elliptical trajectories that are enclosed by the orbits that connect them, the equilibrium points there. Do they get pointy at all, or can they stay this nice circular shape? They shouldn't get pointy, right, because of the constraints of the.
Well, if I were to blow this up, then you may be what you're saying may be precisely what I'm going to show, is that they will have to get closer and closer to a non-smooth set, right? But they would be doing it in a smooth way, because trajectories, if they are solutions of a differential equation, then by definition they are differentiable with respect to time, right? And the time is the parameter that we use to parameterize this curve. So it cannot lose smoothness along a trajectory. Okay, so it will get closer and closer, in fact, arbitrarily C0 close to that wedge shape, but it will never have a singularity or a peak, right? And when it gets closer and closer, it also starts spending longer and longer times near that equilibrium point. So just in terms of the pendulum, if you're really good at hitting the energy levels that put you on these really large amplitude oscillations, then this part of the oscillation will take incredibly long. In fact, in principle, arbitrarily long, right? If the pendulum model that I wrote down was a perfect model for a real life pendulum, then in principle, you could pick an initial condition in the lab for a pendulum that does this for 10 years in principle, and then falls back, right? Or even longer. Well, that's a very thin strip to begin with, by the way. And the second of all, over longer timescales like that, the imperfections, air resistance, damping, all those come into play. But in principle, in a perfect world, 100 years, anything. Okay.
Thanks.
Sure. Anything else? So why would I, was I talking about it? I was just sort of giving still a general example of what we mean in this course by qualitative analysis. This was the simplest nonlinear system. This is in fact still solvable via elliptic integrals, but it's a pain to solve the system. Okay, it's not easy. Well, it's not that bad either, but I mean, it does take a while. And then those elliptic integrals are not particularly insightful. So you're looking at formulas that are complicated. They depend on parameters, the initial conditions, the physical parameters, and there's nothing strikes you immediately from them. Whereas from a few little things, if you know how to do qualitative analysis, you immediately get a lot of properties of the system that, excuse me, either confirm your intuition or in fact, in an extreme case, you can say, wait a second, this model does not reproduce what I know physically to be the case. Therefore, I need to modify the model, because don't forget, all these differential equations are models for something, right? So you ignore often, if not always, something to get to them. And if they don't meet your expectations, then they're not good models. And isn't it wonderful to be able to check those expectations without having to solve this equation for whatever millions of initial conditions, just based on qualitative techniques? So that was the idea here. This is still general introduction. And I think I promised one last example, which I kind of find really cute, about the power of the phase space. So I think within this, if there are no more questions. So this will be just, let's just say example 3 within this discussion unit, whatever it was. So this is example 3. And this is just a nice example of how you can just simply exploit the geometry of the phase space without really knowing barely anything about the system and how much it can buy you. For you, rather. Okay, so here's a story. This is a cute story behind this, I think. So there are basically 2 cities, just imagine them. So this is city A, which would be a very technical term for a city's name, right? Usually it's longer than a character, but this is a math example, so that's okay. And between the 2 cities, we've imagined 2 roads. And the roads can be really fairly complicated. One starts from here, arbitrary complicated, and just imagine it just starts, right? And it really, somebody had this crazy idea, or maybe the terrain is such that you need to avoid all sorts of things to get to the other city, okay? So this will be one road, and along that we can measure the length by a coordinate x1. And imagine that there's another road connecting the 2 cities. Maybe I just denote that by green. They're not starting too far from each other. But again, we know virtually nothing about it. I mean, only know it doesn't cross the other road, okay? But other than that, it can be completely crazy shaped, okay? And along that other road, this is the second road, we have a coordinate, which is x2. So imagine that we know one bit of information, and that bit of information, I move this over here so that I can list that information. So I come here. So I know that 2 bikes. So going from A to B both. So they travel along the same direction, both, right? And they can actually make it from A to B if they work together, meaning that, you know, if they have a plan as to at what speed they're going to be traveling, maybe backing up and so, because there's one thing that we are asking them to do. So this will be can. They don't necessarily do, but they can, if they work together, make it without ever being further away in terms of distance than a distance d, capital D. Okay, let's distance. Why would they do that? Well, maybe they want to be chatting all the way, right? And that's the absolute critical distance within which they can hear each other. Okay, and actually, let's just be a bit, not that it will make a huge difference, but being further away than distance d, in fact, less than d. Okay, I'll just add that. Arbitrarily close to d, but less. Always, and they can make it. Okay, obviously that's not a given that they will, right? Because say one of them starts and then it's already here and the other one starts here, okay, and never makes up that difference. So they can be very far from each other. Or I never specified what their velocities are. So maybe even if they start together, the X1 gets a head start, we're going really quickly, and the other one is kind of trying to catch up, and then they can have arbitrary large distances, right? So mind you that I'm really not getting a whole lot of information about the speeds or when they actually started, nothing, right? And now comes, based on that, can I answer the following question? So this is the question. Given the above piece of information, can two large trucks let's just say carrying mobile homes, so they're really wide. So they're carrying mobile homes of width d. This is the same d. I'll draw a picture in a second. Each pass by. Okay, let's simply make it, so I'll use the same term. When they are traveling in opposite directions. Okay. So the way to imagine the trucks is that you know, here's one of the routes locally, and here's the other one locally. And on this one, the direction of travel is to the right. On this one, the direction of travel is to the left. And I imagine the trucks as boxes, because they are pretty broad, because these are trucks originally, but here's their maybe geometric center, but all of them are, well, both of them are thick. So this thickness that I'm indicating here, these sizes are D. And again, one of them goes this way, the other one goes that way, right? And clearly, if again, I'm not saying if they start at the same time, I'm not saying what their velocities are. So maybe they can actually, but they're allowed to communicate, because obviously both of them would like to make it. They have a delivery to make. So that includes a possibility of one, hey, stop. For instance, see this little tight spot here. So one of them made it here. The other one is coming and starts yelling, hey, can you back up because I need to pass? And then the other one says, sure. So backs up, right? Goes back a little bit. Then the other one can pass, right? And then I go again. So that's clearly allowed. It's all allowed, right? So can we answer this question? And the answer would be normally pretty hard, I would say, because this is the classic case of missing information, right? However, what I do have is, this is a dynamical system. So it's basically the continuous evolution without me really having explicitly a differential equation, but I have a variable, say capital X of t, which has x1t and x2t. okay? And for, I can label both trucks with x1 and x2, except that in one of the trucks, x1 will be growing in time, and the other one from 0 up to some maximal distance, which, by the way, I also never said how long this is or how long the other one is. And the other one, x1, will be decreasing in time, right? And I have absolutely no idea what that does in there. Now, I also, well, one thing, based on the initial conditions, I will say that these trucks are not self-driving. There's continuous communication between the two, so the drivers are operating them, right? So most likely, I should view this as a non-autonomous dynamical system because there's interference from the circumstances. Let me give you one example that maybe truck 1 comes to this point, truck 2 goes into the other point, then they have some sort of strategy, and then it doesn't work. It seems like they're hitting each other, okay? And then they say, okay, let's back up from whatever they did, let's back up and then try again. So when they back up or when they try again, they will be passing through the same points, but then they will execute a different strategy. So just that initial condition for the 2 points at that point does not uniquely determine the future for all evolutions of this system, because next time around, the drivers might decide to take another approach, right? So most likely this is non-autonomous. In fact, it's allowed to be non-autonomous. But the only implication of that really at this level is that when I draw things in the phase space, right, then trajectories are allowed to self-intersect. That's the only thing. That's the only reason. But if I could, in fact, install a navigation system which only cares about the position of the car, and therefore the initial condition would uniquely determine the further evolution, in that case, it would be autonomous. But given that the drivers, not that it would actually change the conclusion, as you will see, but in this case, I want to allow for non-autonomous, which supposedly gives another puzzle to it, right? Because I don't know what strategy the drivers are going to be using, right? So let's look at what's the phase space. So the phase space, and that's pretty much the only thing I know for this dynamical system. So the phase space P would be a rectangle. In this direction, I have x1, one of the coordinates. In the other direction, wow, I entered that unintentionally. In the other direction, I have x2. And those are lengths, but I don't know what this length is, and I don't know what that length is. Nobody has told me. X1 I know is x1 equals 0. I'm at the town A, and x2 equals 0 is a town A, also town A, but along x2 equals 0, when I move away, I move up, this is B. And likewise, along x1, when I hit the endpoint, this is B. And this is the phase space for this problem. x1, x2 as functions of time. So the trajectories I can now draw for both trucks. And the only thing that I'm going to use now, not really use, because I could live without it, but I'm just going to make it even more complicated by allowing self-intersections of the trajectories under the assumptions that this is not some sort of built-in navigation that only cares about the position, but second time around might be a different decision. So therefore, when I draw a trajectory in this phase space, it can self-intersect because at different times the evolution will be different. So let's actually draw trajectories. So one of the trajectories would be for the truck that starts from A and goes to B along this route. Let's draw that. So if I'm a truck that, so again, we're talking about x1 and x2, okay? So it's not just one truck. Sorry, I made a mistake saying that, because the dynamical system is this, right? It's the evolution of the two together, and in fact, they are related. So when I draw a trajectory, then I can't just draw x1, but I have to draw x1 and x2 simultaneously. However, the x1 component will be always growing, and the x2 component will then be decaying, right? So the way to draw that is that I start, x2 starts from B and then goes to 0, and the x1 then grows at the same time. So this will be one of the trajectories. It starts from here and it does something. And because the two drivers are trying different things, it can self-intersect easily. It can be super complicated. But ultimately, it goes to hopefully to the other city, if it can make it, in principle. So what would the other trajectory do? Well, this would be the second car, I have described what the trucks do, and that's the end of the story. This is one particular driving pattern for the trucks. There's infinitely many. So one possible truck pair dynamics, right? So this curve encodes the motion of both trucks at the same time. Okay, of course, I could have drawn this a gazillion other different ways, but the thing is that I would always start from here, and then I was always end there. Now I go back to the only bit of information that I have is that I know that two bikes were also able to make it, but they would start from the same city A and then move towards B. So they start from here and they need to get here up there. So again, the bikes also have a component x1 and x2 and some pretty complicated route. Maybe they had to work hard to keep that distance and they arrive there. So this is the bike pair trajectory. Referenced above. So this is the trajectory of that outcome that I was talking about here, that somehow they figured out a way to do this, to go from A to B without ever having a distance which is larger than D. Okay, so all I did, this is one particular thing, and the red one, because that was given to me as information that this is possible. Well, it's always possible for the bikes to get from A to B, but along each and every point of the red curve, the distance of x1 and x2 is less than D. Whereas the orange curve represents one particular trial of the trucks, and I assume that it has been successful and therefore they were able to get from here to there. Question is this assumption justified? Is it possible? Because that was the question, right? Any thoughts on this? So here's the little fascinating thing, that irrespective of the fact whether these guys actually self-intersect or not, this curve goes from the lower left corner to the upper right corner, and it's continuous. And the other curve goes from the upper left corner to the lower right corner, and it's also continuous. So there has to be at least, possibly many, but at least one point, and I'm showing here several, but at least one point where they would intersect. So they would intersect, say, in precisely one point if their trajectories were this simple, right? But there's always one point where they intersect. And that's just coming out from the appropriate choice of the phase space to represent this. And that's just from the, not even differentiability, just the continuity of trajectories. So I'll just say trajectories are C0. So that means that there exists at least one point of intersection. What does it mean when the orange and the red trajectories intersect? Say here, let's just pick one, for instance. So at that point, look at what the intersection means. The bikes were in the exact same position as the trucks. And that's the answer then, right? Because the bikes were able to make it by never being d or more apart from each other. So that means that even in that position, the distance from each other was less than d. So if the two trucks assume that position, they are closer than d. And look at what will happen then. This this is d over 2, that's d over 2, so they hit each other. End of story, which I still find this pretty amazing. So one point of intersection, then at that point of intersection are the bikes and the trucks in the same position. And that means the trucks hit each other. Because the distance is less than d. Okay, and look at what happens then. So that was a little example just really to show how much more information is encoded in the phase space, and it's always amazes me how little is known here, and yet you can come up with this. This example is taken from one of the books by Arnold. I think I referenced one of them, but I was really amazed when I saw it for the first time. He also references somebody else, a person from Russia that I had never heard of and ever before, but I think it's very insightful. Any questions before we move on to the next one, which is fundamentals?
Yeah, I think you said that the roads can't intersect at the beginning. Is that correct?
The roads cannot intersect. That's correct.
Why is that so necessary?
It's not necessary, I think, because you're right. One could coordinate even in the case of intersection.
All right, thanks.
You're right. Thank you. Mm-hmm.
I have a further question. So it states that without ever being further away than distance d. So would it be possible when the two phase diagrams intersect, they are exactly a distance of d apart from each other, and therefore the trucks do manage to get by one another?
Yeah, well, right, modulo, right? So there will be microns. So that you're absolutely right. That's why I corrected myself here. So I said that's not enough, but you're absolutely right. I realized it as I was right. So they're close.
Okay.
Yeah. My apologies. That's absolutely right. So the distance should be less than. So let me again say that the distance of the bikes, bike 1 and bike 2, is always less than d. Always around that route. Okay. Anything else? All right, so let's go to the fundamentals. By the fundamentals, I mean things that one might absolutely perceive as purely mathematical, pedantic, and so on. Why would I need to know that? Let's just go ahead and solve differential equations numerically, because we can't solve them analytically. They are complicated. So existence, uniqueness, and others can be incredibly useful again in terms of looking at something. Somebody shows you a result and you saying, yes, this is actually possible, or no, go back to your code. There's somewhere in line 2017 or before or after, there's some error, because this just cannot be the case, right? So that's why I'm listing these things for you in a context, not to be super precise in various function spaces, but basically give you tools that you can very efficiently use to assess possibilities, whether something is possible or not, okay, mathematically. So existence, uniqueness, regularity, and of solutions. Now, this is only a question really for continuous dynamical systems, because remember, so this is off, continuous dynamical systems, because for discrete dynamical systems, you have an explicit mapping that defines the evolution rule. So as long as you can evaluate that mapping, sure, you have a solution that exists. Sure, the mapping is by mapping, you know, it's a single valued, it's a function, single valued operation. So if you had an initial condition, each and every point you will have a single outcome. So there's no branching of solutions, right? And then the regularity of solutions then really just comes down to the regularity of that F, that mapping. So if it's smooth, then obviously the dependence of the solutions on their initial location will be smooth, because you're just applying that function over and again. You're building a composite function. So it will be as smooth as the evolution rule. So in that case, in the case of discrete dynamical systems, it's a continuous dynamical system setting now, in which this is by no means obvious, because what you're given is a differential equation, right? So not the evolution rule. So what you're given, in fact, is an initial value problem, as we called it, x dot equals f of xt in general, and x at t naught is x naught. And this is sort of a general setting, n-dimensional, okay? And the question would be, does this, the first question you want to know is that does this initial value problem have a unique solution? Why? Because for practical purposes, non-unique solutions are a pain. I mean, for one thing, if you derived your differential equation from Newtonian mechanics, which is fundamentally deterministic, which says that the past or even the present uniquely determines the future, and then you get a differential equation which has non-uniqueness of solutions, then there's a problem. You made a mistake somewhere. So immediately, that's a reality check, right there. So the first result that I want to recall, and this is a theorem, I'm just going to state it informally, because that's probably one of the weakest forms of existence and uniqueness that you can guarantee, in fact, without uniqueness. So it goes by the name of Peano's theorem. And I can just simply paraphrase is that if this function f, which is the right-hand side, is a C0, which means continuous function, near, which means in an open neighborhood of the initial condition pair, which is the initial location and initial time, then there exists a local solution. I call it phi t. So the phi t being a local solution means that it's a solution. So if you plug it into the differential equation, you get an identity. And let me just carry the times there because they play a role. Phi dot t equals f phi t t. And local, so that's being a solution. Well, not just that, but it has to satisfy the initial condition, because that's what it means to solve the whole initial value problem. But here comes the locality of it, is that t is, for this, is only guaranteed to exist in a small open interval around t naught. So it doesn't mean that I'm guaranteed to be able to extend this solution for all times. So locally, I really have a little cartoon here that just says that if I have a nice right-hand side for the differential equation, which means that it's at least continuous, then in the extended phase space xt, I show this initial condition, which is characterized by t naught and x naught, then there will be an open neighborhood, okay, in which the solution is guaranteed to exist. So this will be your local solution phi t, but by no means can I guarantee that it exists for all times. But you get that relatively easily just by assuming that the right-hand side of your differential equation is continuous, which means it's continuous in both variables in some small neighborhood near the initial condition. Okay, so simple statement, simple result, and what's painfully missing, however, is precisely what I was getting at, that you would like to have a unique solution that you don't get. You get that there is a solution, but there's no guarantee that it's unique. Now let's see if this is just somebody trying to be really precise, because by and large, even in the simplest examples, you will be getting uniqueness or not. So example 1. In this case, and it's going to be something really simple but physical. Let's talk about a free-falling mass. So I think of this mass as simply as a circular object, a ball, if you will, which I release at x equals x naught at some height. Gravity acts in this direction, and it will be falling down because of gravity. So the current position is somewhere here at time t, and I measure that, x, here x, you have x of t. So basically x points in this direction. But not to confuse you, well, yeah, I'm sorry, there's nothing, x is pointing in this direction. But the values of x, given the problem, only makes sense between x naught and xt, right? So the phase space for this problem, as one would naively conclude, is this interval. It's starting from x naught, it's closed from there, and then x is going this way, right? So unless I hit the earth or something else at this point, in principle, since it's free falling doesn't have any limitation in it, it can go, to plus infinity, right? So anything in this direction, in this simple model, just doesn't have any obstacle here. Okay, I really cannot get any simpler than that, right? So how would you solve this perhaps in a physics class? So in a physics class, at least high school physics, to me, was always a bag of tricks, right? Let's notice that, okay? And that always made me nervous, because I either noticed it or not, typically not, but I was told to notice it. So it wasn't quite a spontaneous notice, but a guided notice. So the total energy is conserved because I'm not assuming any dissipation. So if I write down the kinetic energy at any point in time, which if this was mass m, the 1/2 mx dot squared, right? This is the kinetic energy, mass times velocity squared. Then it's really just coming from, since this is free falling and I let it go, maybe I should, so x dot equals 0 initially. So I'm just dropping this thing. So that means that my current kinetic energy is really just equal to the potential energy that I initially had. And the potential energy is equal mg times x minus x naught. I'm sorry, what am I writing here? That I wrote that the kinetic energy is equal to the potential, the kinetic energy, sorry, is equal to the change in the potential energy, right? So when you plug into this formula, then at x equals x naught, the potential energy, which I'm having on the right-hand side, measured from x naught equals 0, is 0. So when the body starts falling, at any point in time, the kinetic energy is equal to the change in the potential energy. That's how I'm gaining energy here. That's where it's coming from, right? There's nothing else that would feed into the kinetic energy. So this is the kinetic energy. And this is the change in potential energy. And again, the only reason that I was hesitating with the sign, because this is not the usual, when we're used to working with altitudes, we probably measure x from this direction, but I have just chosen in this particular problem to launch the x coordinate from x naught and points downwards. Okay, so maybe unusual, but it's okay energetically. So then you say, okay, great. Well, we wanted a differential equation for this, right? So it's easy to get because I can simply solve for x dot. Now I'm going to have a decision to make because I'm taking the square root. So when I express, first of all, I cross out m, right? So then I will get x dot equals, and I know that under the square root, I will have 2g x minus x naught. And x is larger than or equal to x naught. So I have no problem with the sign there. The only question is when I take the square root of both sides, when I get to x dot, what do I write? Plus or minus? And given the way I have chosen x, it can only grow, right? Because I'm falling downwards. So I'm making the positive choice here. So just either don't write anything there or write that. So great, that's a first order differential equation. And on this phase space, which again, if I were to draw it, it looks something like this, right? On this phase space, this is x naught, I'm starting here. And the right-hand side of that equation, let me move this a little bit so that I can graph it. I'll just graph the right-hand side right at that point. So this is x. And this will be, say, y, this is f of x equals f of x. Then the way it looks like, it's a square root, right? So it's something like this. So I'm simply graphing this function. Now this function at this point here is continuous. It's not defined on the other side, given the problem that I have, but relative to the topology of this phase space, which is a, sorry, I need to find, which is actually closed from here. So you could say, how can I have an open neighborhood of this guy because it's closed, the interval? Yes, but it has an open neighborhood in the relative topology of the phase space. The way we find open neighborhoods in an interval, which is closed from one end, is that we use the ambient topology, the R1, which contains that interval. And we define open sets in them because we understand open sets clearly in R1. And then an open set in the phase space will be the intersection of an open set, which is open in R1 with that phase space. So if I take an open set in R1 and intersect it with this half closed interval, then I do generate this set as an open set, right? So if you want to be super technical, then even in terms of the phase space, this is an open set, okay? But even forgetting that, we will say, hey, I'm not interested in these points anyway, because the trajectory is really just going in this direction. So what I need to do is just monitor the graph of this function as I approach this point, and there's no problem with continuity, okay? So this is not really an issue here. Plus, if I really wanted to, I could extend this in the other direction. It would then really be continuous, except that in that direction, it wouldn't make physical sense, the right-hand side, but I can certainly extend this into a continuous dynamical system. So as a result of that, Peano applies. So F is C0 at, maybe you could say x equals x naught plus, if you really want to be precise. So in that open set, on open sets of P, and that means that there exists a solution to any initial value problem. In fact, I could define other parameters here, but there exists a solution. And indeed, if you now think back, this is the solution that we have learned in high school or even in elementary school, that it's just a free falling body. X of t equals initial position x is growing now, plus g times g over 2 times t minus t naught squared. And we learned that. And if you take the derivative of this and plug it back into the equation very, very quickly, then you indeed see that this is a solution, but you might remember this anyway. This is not necessarily how you got to it, right? You knew this before you knew about differential equations. So that's, you could say this is a complicated way of getting there, and you're right. One doesn't need a differential equation, but I still want to consider this as an example that in which if I want, I can derive a differential equation, but I also know the solution. Okay, so you could say, all right, so we were worrying too much because clearly we know from the physics that this is a solution. We also know that there's only one way a free-falling body will fall. So the Peano theorem is just too weak, right? Because it's not guaranteeing that uniqueness that we have here anyway. Now, so the question is, am I right when I say that? From the physical point of view, absolutely. I expect a unique solution. If I get anything else, then I have a problem with my model. Do I get anything else? Unfortunately, yes. This differential equation has another solution starting from the same point, which is x equals constant x naught equilibrium. Just plug it in and you see that it's not changing. So, but x of t identically equal to x naught is also a solution to the same IVP. So we actually have non-uniqueness. So what's wrong here? So this is the kind of thing that I was getting at, that you say, hey, physically, I know that there's a unique solution, right? So why am I getting two solutions? I know that this doesn't make any sense. If I drop something, it's not going to stay there. We have gravity in the picture. How come that it's not falling? But formally, it's a solution. What's the problem? The problem is that this is not the proper way of deriving a differential equation for this problem. Just energy conservation by itself is not sufficient to give a unique description of the motion of a 1 degree of freedom system. Okay, it can be a hack if you know which one to, and you might have learned this, okay, but we ignore this solution because it's physically not meaningful. Well, then your model has a problem to begin with. Because if you don't know what the solution is a priori, if you don't know the answer a priori, which is the reason why we're learning these techniques, that you will attack problems whose solution you don't know, then how will you discount the ones that make no sense, right? So the problem here is that this is a demonstration that conservation of energy is not equal to Newton's law. Conservation of energy is a conservation law of Newton's machinery, which is differential equations. And if you have a differential equation derived from Newton's law, that implies conservation of energy, but conservation of energy doesn't uniquely imply the differential equation, okay? So the reason is the conservation of energy, I'll just be sloppy and just write this. You cannot use that, in generally speaking, to derive the equation of motion. The equation of motion is more than just, I can have different trajectories along which energy happens to be conserved when I draw them, but it doesn't mean that those will be physically realized, okay? So what's the proper way of deriving equations of motion? Well, it's not this heuristics, but then you learn, say in proper mechanics, is that you actually have to derive equations of motion. And here, that's basically F equals ma, right? So in this case, you would have that the mass times x double dot, if x is measured in this direction, okay, then that's just equal to mg. That's your equation. And then m cancels out. And then you have x double dot equals g, which is a second order equation. So the usual trick to convert that into a first order equation, because this is not a form to which Peano's theorem applies, all right? It has to be in this first order form. That's very tempting to do. There's no double dot here. It always has to be, all these theorems are formulated for this system. So you rewrite, you introduce two things. So you know, maybe this is underscore x, okay? And this has x and x dot as variables, so that we have a system which is of the form x dot equals f of x, okay? But that particular differential equation looks like this. Remember, this is the way how we did it for the pendulum as well. x1 dot equals x2 by definition, because the first coordinate of x needs to be differentiated to give the second coordinate of x. And then x2 dot, which is the acceleration, it's not minus g because it's aligned with g. So that's just g, okay? So your f of x, this is together f of x, right? And this has no problem. This has, this is also continuous and everything. But the point, and I'm going to come back to this because Peano will never give you uniqueness, all right? But it also tells you that uniqueness is not guaranteed. But what I wanted to just emphasize that this equation doesn't have the problem that this equation had. Because if I plug in any kind of x naught to this equation, it's no longer an equilibrium point, right? So that because the g is always acting and it's changing x2, it creates an acceleration for x2. x2 is just x dot, so it will move. So this has no fixed point at x equals x naught or x1 equals x naught. Okay, so this is okay, but this is the proper way of deriving it. Proper way is doing mechanics as opposed to heuristics. Heuristics might work, but the problem with heuristics is that you don't know in advance if it works or not, unless you're teaching a class, and then in advance you work out the problem, as I did. But as engineers, we don't have that luxury, unfortunately, or scientists, to know the answer in advance. Any questions? Let's beat this problem beat around this problem a little bit more. But before that, I have to give you a stronger version of the existence, and this is the classic version that we keep using in the dynamical systems. So this is Picard's theorem. And that requires a little bit more. So it's the same setting, but I'll assume a little bit more. I still assume that the function is continuous, but only in t. So I will say f is c0 in t near x naught t naught. So that open neighborhood that I was talking about in space time is now only taken in time. So that means that I fix any spatial variable. So I reduce this from a function of x of t to a function of t. And once I've done that reduction, in the remaining argument t, the function should be continuous. Okay? Still near. Okay? The initial condition, but the second assumption will be different in terms of the spatial dependence. I will assume that f is what's called locally Lipschitz. So the locally Lipschitz assumption. So what's locally Lipschitz? I'll just have I want to underline this. Locally Lipschitz, so that'll be IE. It's basically a function had locally bounded variation, but I didn't say uniformly bounded, but I would say the near, again, I have to say near in X, near X naught T naught. So what that means is that there exists what we call a Lipschitz constant, positive. So this is called in this context Lipschitz And I think it's TZ, right? Yeah, okay. And there exists an open neighborhood ux naught of x naught such that if I take two x values from that neighborhood, so for all, I think I call it x tilde x, but let's for all x tilde taken from this neighborhood. So I'm gonna just take all possible pairs from this neighborhood. When I check the difference in function values by keeping now time fixed, so it's the same time, I'm not varying time. I've already made my assumption about time, but then I fixed time for the purposes of defining Lipschitz in X. And I have two of these. And I take the absolute value of this difference. Then it should be less than or equal to this Lipschitz constant times x minus x naught, right? And near that should be, for times, it's unrealistic to expect that this will be uniformly valid for all times, but at least for times near the initial time of interest. Okay. So what does this mean? So it means that somehow the variation of f is bounded in a more abstract sense by a cone. So locally, if I draw a picture in space time, so this will be x. This is, sorry, it's not in space time. I'm basically graphing y. This will be not in the phase space, but I just want to sort of sketch the types of functions. What just want to sketch what the Lipschitz assumption means. If this is the line, say, well, you can take this in an abstract sense. If these are one-dimensional variables, then this is what I would have as two bounding lines for the local variation of the function. So if the function, I'm showing that if this is here x naught, this point in x, then what this constrains the function is that for short times, t is the parameter that changes along the function. So for short times, whichever way the function varies, right? It cannot exceed, it cannot get out over these two lines. And the lines would be, again, in 2 dimensions, this line would be, let me use the same color. This would be sorry, y equals L times x minus x naught, where you see that Lipschitz constant appearing here. So the basically L characterizes the slope of this line. And then you would have y equals minus L times x naught, right? Because this is a constraint about absolute values, and the function would have to fall between the two. Now, if these variables are n-dimensional, then you have something a little bit different, because this is then really defining a cone, which I will just maybe indicating like that. Because we're talking about distances now in a high dimensional space. And then when you work that out, it's not just two disjoint lines, but basically a line bundle going through the origin, right? So that's why I didn't write here y equals minus L x minus x naught, because the one-dimensional case is degenerate. In one dimensions, or if depending on whether you view this as one-dimensional or two, topologically a cone degenerates into two disjoint lines, but when you start allowing more dimensions, then it really becomes a cone. So basically, you need to be able to define a cone which locally at least contains the function, and function doesn't get out of it. Now you're allowed to have a larger L if you need to have, but there's got to be some L that does that locally. So that would be the idea of Lipschitz. And one thing to note is that if something is differentiable, then it has a derivative. And if it has a derivative, then it will only gradually depart from that derivative, right? That locally defines the slope. So just to be on the safe side, take twice that slope in both directions, and locally you're going to be fine because you will need time to get out of that cone. So if something is differentiable, so it is a well-defined tangent, then it has to be tangent to that tangent, then you will always be able to pick a small enough cone that contains this, right? So if something it does have a well-defined slope here, so it's at least C1, then you will have the local Lipschitz condition, which I think some notation for this is the local Lipschitzness follows from C1. It also turns out, because if you then really shrink the size, if you get closer and closer to the tip of this cone, then this means more and more limitation on the function. So since the cone is going to 0 in terms of its diameter, the function also has to go through x0. And the closer you are to x0, the closer you have to be in terms of the function value to x0. I didn't say what the function, here the function value would be, say f of x0 at this height. So here, it's not y equals 0, but y equals f of x0, right, down here. So because of that what I have just pointed out, it follows that if you have Lipschitz, then by all means your function must be continuous. So C1 implies locally Lipschitz, and locally Lipschitz implies C0. So local Lipschitz is a nice in between C0 and C1. So it's an intermediate category. This means that if your right-hand side is C1, so it's already differentiable, then you already got uniqueness, no problem. However, if it's C0, then you don't have uniqueness, only Peano's theorem applies, okay? So when you ask what's the optimum between, do I really need to have C1? No, you don't. You get already existence and uniqueness for something in between, and that's the local Lipschitz condition. So let's, can we think of then actually something which is locally Lipschitz but not C1? It doesn't have to be some super whatever nowhere differentiable measure.
Absolute value function.
Exactly. Yeah. Great minds meet, because that's exactly what I had in mind. Okay. Thank you. So the example. So this is y and x, and then I simply just take the absolute value function, which has a slope here. And of course, it doesn't have to be actually symmetric. You take absolute value here and 2 times absolute value on the other side. The point is that it doesn't matter, but you have to have 2 finite slopes, because then you pick any 2 points and you evaluate the function values between them. Then the largest of the 2 slopes will always be an upper bound, no matter where you are, when for the change of the function. If you are on the same side, say here and there, then clearly you're actually even reaching that upper bound rigorously, right? For the slope, the possible slope. So this slope would be then that. But even if you are, then clearly if you're on the other side, the same deal takes place. If this is really the good old classic absolute value function. But the nice thing is that even if you are on different sides, which I just indicate here, then see for these 2 points, for instance, you know, I go up here and I go up there, the variation in the y direction is tiny. And of course I can position myself to make it larger and larger, but the slope will never be larger than this. It will actually, I will reach that slope only if I'm pushing one of the points exactly to 0 and the other one on the other side, right? So this is the example of a function which is continuous, but not C1, and it's Lipschitz because it has a maximal slope. So then let's go back actually to my failed attempt here to do Newtonian mechanics. So go back, so example 1 revisited. Basically, let's see what went wrong. So remember the heuristically derived differential equation was this. And the initial value problem was then the two together. So what was the problem here? I think we see the problem now is that if I now look at the right-hand side, the same way I have looked at here. So this is x and this is y of equals f of x, with f of x being this right-hand side. And that's a square root function. And that is certainly not differentiable at that point, because at x naught, because the slope of the function would actually hit infinity, right? Not finite. So there's no finite slope. But not only that, so it doesn't have to be differentiable to be Lipschitz, right? Because it's less than differentiability. But nevertheless, Lipschitz requires, just pictorially, that I should be able to box in somehow this function locally into a cone, or in this case, between two lines. With this choice, I clearly haven't succeeded, but one could argue, well, just make it larger. Well, if I make it larger, I'm not succeeding either. The problem is that there won't be any cone of finite slope that I can draw here that would contain this line, because it comes in with this infinitely large slope, right? So that's not Lipschitz. And that's why uniqueness cannot be guaranteed. But if I now go to the correct formulation of this problem, get this. So that is, in fact, the right-hand side is a linear function of x2. As such, you don't even have to check the cone business, but you know that any linear function of x2 is not only C1, but C infinity as effective and analytic. So clearly you're safe. You're very much on this side of the spectrum, right? You can write C to C. So when you have a very smooth function, that's automatically local Lipschitz, and then you have the uniqueness that you want. Okay. Anything else to be discussed about this example?
I think someone spotted something in the definition of locally Lipschitz. Could you check the right-hand side?
Thank you.
Are you sure about the x naught
Yeah.
and not being an
Yes, thank you.
tilde? Yeah, credits go to Simon. He spotted it first in the chat.
Thank you very much. That happens a lot, that I say one thing and write something else because I'm already thinking about something else. Sorry about that. That can be very confusing. Hopefully it's clear now, right? Thanks. All right. Anything else? Then while you're thinking, so we have now a powerful tool that by inspection guarantees uniqueness. And again, by the same token, if you are not in a position to be able to apply Picard's theorem, and you are in a physical setting in which you do absolutely require uniqueness, otherwise your model is wrong, then your model is wrong. Okay. So that is something, there's one of those things, you look at it just by inspection and you tell somebody that no, that's gonna, or somebody tries to blame some numerical effect or interesting behavior that they got from, oh, potentially it has non-uniqueness. That's the explanation. And then you say, cannot be, because the right-hand side is smooth. And before you say that this is a hypothetical story, I'm saying this because it did happen to me as I was a PhD student out of all places at Caltech. And my TA was very knowledgeable, but he worked in mechanics and vibrations. I went back with a problem to him that somehow it turned out the problem statement wasn't right or something. And then I told him there's something not right here because, and then he said, looked at it, okay, then must be something. So this equation has no unique solutions. And then I exactly said, it's not possible. So that's one application of Picard's theorem, is to make a good impression very quickly. But that's not the main application. Main application is to verify models just by inspection, not the total model, but at least their fundamental. It's basically a safety check or a reality check that doesn't justify the model, but at least excludes it being obviously wrong. So the geometric consequences that I wanted to talk about very quickly. So we already talked about this, but now it's been firmed up that trajectories of locally Lipschitz autonomous systems cannot intersect in the phase space. And I was also part of something related to that personally, but on the receiving end, because I still remember that in my first ODE classes, this was one of the reasons why I almost failed the class, because I was required to draw phase portraits of an autonomous system, right? And I was drawing all these curves and everything, and unfortunately, several of them were self-intersecting, and that's never a good thing for a system that's locally Lipschitz. In fact, it was even C1. So essentially, I almost failed the class, but the professor gave me another chance, right? And now I'm teaching ODEs. That says something about the system. If you don't know it, you teach it, right? So, what that means is that on the level of a picture, that again, if you have a general multidimensional phase space. So I'm showing one of the coordinates here, x1, and then the remaining ranging from x2 to xn, and you somehow come up with numerically or qualitatively, as I did back then, with something that would show solutions that are complicated. And the only way you can really somehow make that phase space work, because you have so many constraints, is something like this, that two solutions cross, and the point that and the crossing point is not an equilibrium, but it really cross, that this just cannot happen. So this cannot happen. The only resolution would be is that the crossing point where they cross must be an equilibrium. So the note is what we have seen at the pendulum, that this is possible. The following is possible, that apparently you're getting some intersection of trajectories. Okay, you see that, there's every indication of that. Then you can immediate, and this, you can establish with fairly low resolution as well, right? Because we're just talking about, even if this is a polygon, because you're doing this numerically, you clearly see that they're intersecting at some point. So the only way that can happen in a system that's at least Lipschitz is that the intersection point itself must be a trajectory. So that's a trajectory. And the one set of trajectories in that case is in fact running away from it. And very often this is just one particular situation. The other set of trajectories is running to it. And in that case, the fixed point is a separate trajectory. So nobody is intersecting anybody else. It's just that trajectories are approaching each other infinitely with infinitely high accuracy. That's allowed. There's no problem with that. But them crossing in a finite amount of time, that's not allowed. So and still we have to remember that for non-autonomous systems, it is possible to see intersections. So for non-autonomous systems, which means that the evolution rule explicitly depends on time in the extended phase space, the intersections are possible in the phase space. And why is that all of a sudden? Well, it's because that it does not contradict uniqueness of solutions. Because if this is, say, x1 and this is x2 through xn, I can easily have a trajectory which just evolves like that. And when it is apparently self-intersecting, or actually in the phase space it's intersecting, it simply crosses that point at different times. That would be the case here as well, of course. You can attribute different times. You know, you could say this is autonomous trajectories here now and it's coming back, time has elapsed. But the evolution rule, you know, the autonomous systems does not depend on time. So once you're at this position, you have a unique evolution because you have a unique tangent vector governed by the differential equation x dot equals f of x. Right? So you have a unique tangent vector, and it doesn't matter at what time you show up at that point, that you will always be following the tangent vector. That's not the case here, because that tangent vector to your solution does have a dependence on time. So when you arrive there next time around, right, I would say this is T1, okay, and then time is going, and I'm here now. Nobody says that I have to follow the exact same orbit, and therefore I actually have to be on a periodic solution. No, you're basically crossing that same point at different times, and therefore the right-hand side takes different values. You will have different, first time around you have this tangent vector, second time around you have that tangent vector. Even in that case, however, there's a construct that removes that inconvenience. So for such systems, trajectories will not intersect in the what we call the extended phase space, which we often use in dynamical systems because of this convenience. So trajectories do not intersect in what we call the extended phase space. And the extended phase space is really just space-time or phase-time, right? Which means, I wrote that out, no, phase space. And that extended phase space is just the original phase space, P, Cartesian product with time, R, right? So you're adding simply time as an axis. Now, technically, so how do I know? How do I know that that they will not intersect in that extended phase space? Well, it's a simple trick, because you will say, okay, the variable, I'm going to introduce the dynamics, a formalism that describes the same dynamics, but now in the extended phase space, I introduce this large x, which is little x and t. And this is then an element of the extended phase space. Okay? So that's the one thing I'm doing. But then the other thing is I'm interested in the evolution of x of this extended variable in this larger phase space. So the evolution of x dot is what? Well, I just go ahead and differentiate its elements. X dot, and when I differentiate t, then I just get 1, because I'm differentiating with respect to itself, right? So I don't know what it is, then x, I know what it is. This is then f, x, and t, right? That was my autonomous system. And then 1 here, but now I'm defining this to be capital F of X. And I can do that because these two variables now together form my large variable X. So ultimately, this right-hand side only depends on F of X. So then on this extended phase space, I obtained an autonomous differential equation. And if the right-hand side was locally Lipschitz, the one here is certainly not going to change that because one is as smooth as possible. So if F was locally Lipschitz, then clearly F is also locally Lipschitz. And hence I have uniqueness of solutions. But now this is an autonomous differential equation. Therefore, I cannot have intersection for this one now in the extended phase space. And the extended phase space looks at something like this, that I can again, look at the variables. This was x1 and this was x2 through xm, but now I have time as well. So what you see here is the extended phase space. This is P cross R. This is the extended phase space. And in this extended phase space, this whole capital X evolves. And it cannot, all right, it looks like it's intersecting, but it's like a helix, right? So it's not intersecting. This is capital X of T. I put these little marks here that you see this is a different X. So that's a tool that we often use in dynamical systems. And to make a long story short, every non-autonomous dynamical system can be turned into an autonomous dynamical system with all the good properties of that. So why don't we then do that? And why don't we even just talk about non-autonomous systems? Because they can all be made autonomous. The sad answer is that, yes, that is true, but it comes with a price. First of all, I have enhanced the dimension of the system by 1, and that very often, most of the time, that doesn't help if I now have to analyze a larger dimensional system. But more importantly, usually where things go wrong is then I have now unboundedness in this variable. So no matter what, in the t direction, I'm just going to grow. And a lot of the results, a lot of the important results in dynamical systems assume that you have some sort of compact set that contains the trajectory. And in this extended phase space, you will not have any compact set containing the trajectory as it grows, because you always grow out of it, right, with time. So that's the reason why it does help, actually. I'll show you examples in which it does help. Okay, anything else I should mention about this, or any questions? Very quickly, I think the one thing I'd like to mention, another subject which is good to be aware of, is that I first used the term here, local existence, local solution, right? When I was talking about Peano's theorem. And nobody had a question about it. So I asked that question now. Where was that? See, local solution. And I said, oh, I really have to be careful because the solution might not exist for all times. And again, this just might seem like mathematical pedantry. Why wouldn't it? Why would it? I mean, is the right-hand side keeps being smooth, right? So then, all right, okay, maybe locally it exists, but then it's still smooth there too. So I'm just going to continue it, right? And then why cannot put together a globally existing solution? And unfortunately, things are not that simple, because that domain of existence that I can certainly extend solutions a little bit, but who's to say that that open set, as I'm in the process of extending, who's to say that it's not shrinking to 0? And it keeps, and then that means that I can do the extension, but for shorter and shorter time. And in the limit, I just cannot do it anymore, right? Because I'm hitting some sort of magic wall. Is that again just sort of is it just a hypothetical situation? It doesn't happen. So let's talk about that a little bit. So local versus global existence. Now this is again something very important in practice, because there are lots of cases when it seems like in a numerical code that the solution doesn't exist globally. Namely, it blows up. In MATLAB, if you have played with MATLAB, you can easily get this very annoying message NaN, or your variable at point is no longer a number, but NaN is a non-numerical NNA, no? Non-numerical argument, or no, it's NaN. Who knows what that is? So what is it?
Not a number.
Not a number, thank you. So it's simpler than I thought. Not a number. I used to get that a lot, right? So then there's two explanations. You either have to use better precision, or there's something in your code, or intrinsically your system just cannot be controlled, and the solution ceases to exist at some point, and you have to contend with that possibility, right? So it is of advantage clearly to know whether this is happening because of your numerics, or there's something built into the system that you're trying to fight, but you won't be able to declare victory in the end. So the local versus global existence question. And let me start with an incredibly simple example, which will underline that this is a real issue. I said the simplest physical nonlinear system is the pendulum, but the simplest physical dynamical, the simplest nonlinear dynamical system is certainly not the pendulum. It would be the following: x dot, and I don't write a linear term here, which would be the simplest, linear equation would be x dot equals x, but I write x dot equals x squared. Now, it doesn't really get any simpler than that, and I just can't see why this could not be the physical model for something. Right? Just as simple, I would say, okay, my first guess for this nonlinear problem as a model, it would be this: x dot equals x squared, and I just pose some initial condition. I could pose it as 0 because it's an autonomous system, and I just say that initially this is 1, right? Now note that the right-hand side here is as nice as it gets. It's non-linear, but certainly f is CR for any r larger than 1. And even you could pick r equals analytic, which is, so you could say r infinity, so it's C infinity, so r is arbitrarily large. But this function is even analytic. Just recall what's analytic. Analytic means that its Taylor expansion is convergent, so it just returns the function. In fact, this is globally analytic because the Taylor expansion is just what you see here. It's the second order term. So it's as nice and actually nicer than most functions that you find in modeling, right? So the very least we would expect that this has, once it has a solution, so certainly it has a unique local solution, right? That's what Picard guarantees at this point. And why would we not be able to continue that, right? Well, this is a separable ODE, so I'm not going to go through the solution of this, but formally we learn, although this is sort of an abuse of notation, but we learn that we write x dot equal as dx by dt and then multiply both sides by dt, right? So that's sort of an abuse of notation, but this can be justified after the fact. So you basically, you write it in a way and then you integrate both sides. And when you do that, then you get x of t and you plug in the initial condition equals something really simple, right? 1/1 minus t naught. And you differentiate this, you plug it in, you will see that this is a solution, right? You differentiate it once, you get the negative of this squared, and by the chain rule, you have another negative sign there, so the two negatives cancel out. So what you will get is 1/this squared, but that's just the solution squared, because this is the solution. And therefore, the right-hand side is what it has to be along the solution. So here comes the issue that I said at time t equals t naught, the solution is 1. This certainly has that property. So this is in fact the solution already solving that initial value problem. So at the initial time, this is 0, but then it starts growing. And as it starts growing, you will see what happens. Very soon, it's going to hit 1. And when it hits 1, even before that, goes to infinity. So even in this embarrassingly simple example, and as smooth as you want, even globally analytic, if I plot the solution in the extended phase space, and I start from here, so this was T naught, and this is 1, this is where I started from, then at the time, T naught plus 1, it blows up, no matter what. Blows up means that it never reaches that point. It just goes to infinity. So this is called the blow up. So it can easily happen. And, you know, by the way, then if you're any reasonable solver, then that will blow up too. And you will get the NAN, because after a while, the number will just be so large that MATLAB will not be able to store it in any finite arithmetic form. So then you go to infinity. But that is not the problem with your solver. In fact, it's your model that has that intrinsic property. And again, it makes you wonder whether this was the right model to begin with, because if you know that the physical process that you're modeling is bounded by nature, because for one thing, it's bounded in a box. Suppose it's some sort of fluid flow, and this is the position of that. Well, fluid is not that easy, because in fact, in 3D, we don't have global existence. We don't know yet. It's worth $1 million right now. That's one of the Clay Institute of prizes. Even if you just make substantial progress towards it. But in 2D, we do have global existence for fluid motion. So suppose you're confined to a 2D container. We know that the solution exists globally. And in that case, that's a good thing. But in 3D, we don't know a priori. So even if you are in a container, in principle, the Navier-Stokes equation is such that certain derivatives of the velocity may blow up. We don't know that in advance, right? So that's a possibility. But in 2D, if you're running some sort of OD representation of a flow in a bounded domain, or even unbounded domain, you cannot have any blow up. So if you do get a blow up, you know it's coming from the numerics. But if you then step out to 3D, people are still investigating that. They get all sorts of indications of possible blow up, and it's not coming from the code. So let me stop there. And that's where I'll pick up tomorrow, and then we'll just continue. We have a few more fundamentals to cover, and then we start building the sort of this geometric view systematically in the phase space, starting from equilibrium towards more complicated structures. Any questions?
I have more organizational questions, so if anyone has any questions regarding the content, then they should go first.
Okay, so if not, then please go ahead with your question.
So I'm an applied math student. I'm taking this course that's listed as a prerequisite for nonlinear dynamics and chaos 2.
Correct, yeah.
However, this one I don't think it's offered in the applied math master. Is that true? Are you aware of that?
I believe that it should be offered, and I had a discussion whether this can be one of the courses that can be accepted for credit, or you guys have a list of courses that are possible to take to satisfy certain requirements. And a student pointed out to me last time that this one isn't. And there's a historical reason for that, because for a long time, the applied math, the math program had their own dynamical systems course, and they didn't want any competition to that. This is not my opinion, I was told at the time. Now, if there's still a dynamical systems course in the math department, then most likely they don't want this to be listed, because but if there isn't one, then there's no reason why it shouldn't be listed. If it's still not listed, I'll go back and ask the people why it's not listed. But thanks for the heads up. It should be.
Because I just checked, and it's not listed as offered there, and it could just be that the stuff online is old. And I'm like 90% sure that there's no dynamical systems course, because I thought that was done by Mary, and he's doing something else this semester.
Right. Even when there was one, it was actually very, very abstract. Mostly, what was it about? Measure theory. So the type of dynamical systems that is borders with pure mathematics, and this was more of an applied math course. But you're raising a good point. I'll get back to them again. Now I have to say that strictly speaking, the requirement for nonlinear dynamics 2 is nonlinear dynamics 1, nonlinear chaos 1, or equivalent. So if you have a course from elsewhere, or even if you're sitting in this course and you have seen it, then you're satisfying the requirements. To be honest, I haven't been checking the requirements strictly. So if somebody comes and declares that they are prepared for nonlinear dynamics 2, then I'm happy to have them in the course.
All right. I just checked it out. There's no dynamic systems from the math department.
Okay, so let me then, since you're the second one raising it in the past 2 years, I got a first reaction, very strong one last year, but I'm raising it again. Okay, because I think you're absolutely right. This, I mean, I taught this course when I taught this course at MIT, at Brown, and McGill. It was all not only applied math, but any math student was able to take it for credit. This is the first time ever that this happens.
Yeah, and I actually really want to take the course. It's not just I want to do on the side, and I'd rather not substitute it for something else.
Yeah. Okay.
Limited amount of time, and I'd really like to spend that time doing this course and not something else.
Yeah, I appreciate that. So let me talk to your department again and see what happens. This is now the second time I'm hearing this. All right, good point. Thank you. I'll make a note for myself.
Do you have an idea about when? Because otherwise, I do have to book another course. And
oh, like right now, after class, I send an email again.
That's
okay.
Right.
All right. Thanks.
And then I guess I'll get an update tomorrow or next week or something.
Yeah, right.
All right.
Let's hope for it. I mean, these things do take time, right? So I don't know how.
Yeah, there's all the bureaucratic stuff. So I mean, yeah. I'll list backup plan, but I'll.
Right. I mean, one thing, you're not part of the computational science and engineering program. It's really you're in applied math, right?
No, I'm applied math.
Because the thing is, a case can be made. I'm affiliated with the computational science and engineering program, but not with applied math. And okay, so that might be a harder sell, but I try. Thank you.
Evolutionary dynamics, and that counts towards my applied math master, but this doesn't. So.
Okay.
I think that is a little bit further away from applied math than what we're doing here.
So evolutionary dynamics.
Yeah.
What's that course about?
So first lecture is on Friday, so I don't want to speak too much that I don't know about.
But generally speaking, because I don't know what it is, that's why I'm asking. I'm just curious.
More like it's a theoretical approach to evolution. So the first lecture is Lotka-Volterra equations, simple bifurcations. When you have like you get the reproducing. You have a population which reproduces, and then you get the bifurcation of the period, and that sort of thing. And so I mean
that sounds like even a more applied dynamical systems course than this one, because it's applied to
specifically applied to biology, and the math is less complicated because it's part of the biology department, and so the students they're only required very basic linear algebra, and I mean I have a friend from biology who's taking it, and they've never seen PDEs, they've barely seen ODEs, so
and that's accepted. Okay, interesting.
I just hope that I don't get both of them taken up, because I would like to take both of them.
Yeah. Okay. No, that's important. Thanks a lot. I appreciate it. I'll try to get an answer soon.
Yeah. Thank you very much. Fingers crossed.
My pleasure. Yeah. Anybody else? Okay. We're done for today. Have a good evening. See you tomorrow.